welcome all. I would like to welcome you to New Friday Seminars for semester 1 in 2015. And our first presenter is Dr. Stephen Gay. It was nice of him to actually be our first speaker. So welcome. And he comes from MIDAS International, and he will present his work on holistic modeling of mineral processing plants, the MIDAS approach. So, Stephen, the floor is yours.
Thank you, Vladimir. For a start, I'd like to also thank Emma Beaumont, who I'm not sure if she's here, but who's basically trying to instigate an alumni, so to try and get more communication between the ex-staff members and the current staff members and students. I'd also like to thank Chris Moran for allowing me to give this seminar. Just a little bit of background about me. I actually come from an applied mathematics background. I studied at the University of Queensland. I then did a master's degree in geology and geophysics, but actually just oceanography. And then I had the dream job, which was sail design, actually simulating the design of sails for the America's Cup in 1986. Unfortunately, the syndicate we worked for wasn't the winner. I then moved on to simulating ocean currents at the Australian Institute of Marine Science. And whether it was a stroke of madness or not, I decided that mineral processing sounded pretty interesting. And so I was offered a PhD. In fact, that was during Tim Napier-Munn's time as research director, and worked in the area of stereology, which is translation of information from 2 dimensions to 3 dimensions, and it's actually relevant to this particular seminar. And at that time, Bill Whiten was one of my advisors, as well as Jeff Lyman. So I've been able to at least have a really great technical relationship with Bill Whiten now for about 25 years. I worked here as a research fellow and later senior research fellow, developing mathematical models. I felt I actually achieved a lot when I was here, and I also felt that the best way to try and make the methods that I developed available to the industry was to actually go independent. So in 2008, I went independent. I started my own company of business, MathsNet, and for about a year I worked for contract, which included JKMRC. Then in the process of trying to get contract work, I was actually offered a full-time job in Toronto with SGS, which indeed seemed like a dream job, but the reality was a little bit different. So in 2012, circumstances at that time meant that it was actually fairly easy for me to go back to contract work. So I went back to contract work in 2012, and I've been basically independent ever since. In 2014, some of the ideas which I've developed, which I will be explaining in the seminar, I realised they were patentable. I consider that they're valuable, if not very valuable. At the end of the seminar, you can give me your own opinion as to how valuable they are. I believe they'll change mineral processing and analysis. So I patented the approach, and I actually at that time was looking for government funding and investors, and so I set up a new company which is called MIDAS Tech. It's actually Midas, because it's related to a famous Greek story of the man who whatever he touches turns to gold. Of course, MIDAS actually means Mining Industry Data Analytic Service. But there is a certain element to this seminar of trying to get something for nothing. And I hope you'll see the connection. So the MIDAS Tech itself has 2 main product streams. MM Plant Monitor, which is really the mineral processing software and service. And the mining industry is tough at the moment. So in the last few months, I had my boys. My boys, sorry, I should just say, about 10% of the audience probably know me from being a staff member. And so I know my boys as little kids about here, but now big kids up here. 2 of them are doing university, biomedical engineering, and the third is grade 11. But we decided that for their holiday break, it was their own decision as well, that we might actually try and develop a general Excel flowsheet system. There was none which was available for download, and this, we all know that LIM is an Excel flowsheet system, but it's just for mineral processing. I wanted to make something fairly general which could be used particularly in oil and gas, civil engineering and financial modelling. So we're actually going to start marketing that in the next month to try and bring in some steady financial, bring in some steady money, so that I can then focus on promoting what I think is the most valuable work, which is the MM plant monitor. Masonet still remains as a business for independent contract work. So within the MM plant monitor, there's actually about 20 different components, but loosely I refer to MM Visio Bout as the mass balance system and Visio Sim as the simulator. Why I have Visio is because I actually use the Visio flowsheet system, which I'll discuss during the seminar. So to start the seminar itself, I'm heavily into LinkedIn. I know I'm connected to about 10 of you in LinkedIn, but I find it is quite valuable for having discussions. In fact, when it comes to the Excel and VBA groups, it's hugely valuable. I wouldn't be able to get anywhere had it not been for LinkedIn. But if you go into some of the mineral processing sites, you may well get the question, what is the best simulator? Now, they don't really clarify what they mean, and because there's lack of clarification, they generally get one-line answers. So someone writes in and says JK Sim, another person writes in and says JK Simfloat, and it becomes a very superficial type of conversation. And of course there's USIMPAC and LIM and so forth. But there's no way I would respond in such a one-line-ish type of approach. So I tend to say, what are you trying to do? What are your requirements? What's your budget? And really, what does your company do with the simulator and so forth? So I generally respond in levels of depth, for which I actually get quite a lot of responses privately. One of those responses was from a now colleague, Basdu Rupal, who provided a one-day course in simulation in South Africa. And he asked me to critique his course on simulation. I provided honest feedback and he could handle it. And I said that a one-day course is inadequate, that I don't know what you're trying to achieve in a one-day course, but you provide the participants with some sort of exposure, but really, what will they absorb within one day? What we need to do is a 5-day course in simulation. And he said, well, that's a good idea, Stephen. You come to South Africa and give the course. And so it started me giving courses in simulation in South Africa. And he said that it would lead from one course to another and so forth. So I thought, oh yeah, well that's fine. I'm doing training courses. Sounds great. I didn't realise it would take me about 3 months to prepare. I had no idea. Oh, Tim's nodding his head. He knew full well what I got myself into. So I had basically a 3-month stint, and again, I was slave driving my boys as well to help me because I was just running out of time. But it gave me the opportunity to really think about a simulation, particularly if you're trying to present it to people who you actually don't know who they are. They could be operators, they could be financial people, or they could be researchers. So it was quite a challenge to come up with the first course. Obviously, once I've done the first course, the successive courses aren't so hard. But so there's been 2 periods in my life where I really had to think hard about simulation. The first was at JKMRC, when I was in the JK Synflate group, which was led by then JP Francis. And this was the second time. And it no doubt has influenced me about my eventual development of software in MIDAS team. Now, when I respond in detail, and this is actually the opening to the course, I probably should just break in. Some of you have already picked up some pancakes. We've just left some material there for those who are interested, the software itself, and also the course. The next time I will be giving this course is actually in the Minerals Engineering Flotation 15 in South Africa. So if any of you happen to be going there and want to spend 3 days doing a simulation course, may I encourage you to attend. But basically, this is the opening way that I discuss simulation in the course. Now, this particular seminar, there's two purposes of it. One is to actually provide an overview of the course, and so I've taken what's now a 6-day course, and I'm just giving you an overview in about half an hour. And the second part is to actually show the new methodology, which I'll explain. But when we think of simulation, what are the requirements for a simulator? And so in the course itself, I provide this as an opening and get people to discuss what their requirements are. And it's really useful for me because I actually just sit and do nothing. And which is really, it's really important when you're giving 5 days worth of seminars to just sit and let the audience guide themselves. So they generally get into this, and for about an hour they'll discuss what their requirements are and everything else, and I'm furiously trying to take notes. And but these were my criteria. So I'm actually not going to go through this in depth because I am conscious of time. I should just add, first time I went through the seminar was 2 hours. I halved it, then it was an hour and 20, and then I halved it again. I haven't actually got through it because it's just so much I want to say. I could talk for 6 days non-stop without a problem. So it must be part of this total solution, and it has to have good reporting. But point 5 is that in some way the simulator needs to appeal to everybody, and that's also point 4. It has to cross the various structures within the organisation. And we'll discuss that. Obviously, comments, robustness, and accurate, etc. And point 12, for me, it must be extensible. And what extensible means is that the user can put their own models into the simulator. And so if we were to consider those various criteria and mark it against various simulators, you could self-score where you think those simulators lie. And I think in terms of point 12, the most visionary simulator was Lean, or is Lean, which is Dave Wiseman's system in Excel. And he branched off specifically to make a simulation system which users could add their own models. We'll also discuss that as we go through. It was also part of the course and also part of the paper. I had to come up with 9 steps of simulation. And basically in this, I haven't seen any book or paper which actually describes exactly what you need to do in order to improve the performance of a mineral processing plant from an analytical viewpoint. So I've basically put these 9 steps, and in the course we go through it. Now the first one, most of these of course are non-original. You would be more than familiar with them. So understand the flow sheet, data collection, data collation, mass balancing. But really where the MIDAS tech niche is influence. That's where we will focus on later in the seminar. Defining operational variables, model fitting, simulation, and optimization. This particular course is now split into two 3-day courses. The reason for it was that the course itself, the latter part, really started to input a lot of the ideas which I valued and that was confusing to people because I needed to differentiate conventional methods from what were the methods that I specifically advocated. So basically I split it into 2 3-day courses. So the basic course really goes through conventional simulation skills in mineral processing, and the advanced course is where I really dominate the type of style and the advanced styles which I believe are required. And so I actually say that in the advanced course you actually learn what's not available in the literature, papers or lecture notes or books. So, and from that there's been a number of derived variations of the course, mineral processing monitoring strategies, and as I said, flowsheet simulation in Excel, and a very basic course is Excel for metallurgists. My particular software is in Excel, and so I do explain concepts in Excel, and we often find that we might get bogged down because we have to teach basic Excel skills to students. So we actually, in the last course in South Africa, which I found incredibly hard to manage, on one hand we had professors, on the other hand we had operators who really weren't that comfortable with Excel. So it really did require to be separated. Now, this gives you a general idea of what's covered in the course and the time period required to discuss various concepts. Now, this isn't the time for the seminar now, so don't be too worried that you don't have to say to your wives you'll be back in a week. But we're just going to run through it quickly, what gets discussed in this course. And I think there's been a change from my times at JK. I think because of being able to give the simulation course and also really regularly talking to the industry, I've got a it's an interesting insight I have into what the industry actually does. So I think it will be informative if I just go over this. So point 1 is understand the flow sheet. Now, just mention briefly that on flow sheet systems itself, near 20 years ago, I really wanted to link up the flow sheet system with the mass balance system. And I did quite a lot of research on flow sheet systems. And after all this research, I went down to Harvey Norman, which I don't think exists anymore, but did exist at Indooroopilly, and bought Visio Technical for $45. So there existed pretty easy flow sheet systems which you could integrate, but with Visio Technical, you had to learn how to use the VBA to actually understand how to convert what's a drawing into a connection, into a understanding of streams and units. But I show the participants Visio. You can download trial versions, and they actually explore flow sheeting and also explore VBA and what's behind the flow sheet. Now, when it comes to data collection, I've always presumed that mining companies collect data. And when you talk to companies, they'll say they indeed collect lots of data. But when you actually ask them, have you done a plant survey, you sort of get blank expressions. Do you have size distributions or assays? Oh, only of the final kind. But the plant auditing is almost an outdated skill. And that's, Michael Hayes is my colleague. He has lots of plant experience. But in future, there'll be far more emphasis on data collection. Now, in terms of simulation, what I want the point here, the key point is that simulation is step 8, and it's only one part of a whole solution. It's not isolated anymore. It is common. I do ask companies, do they simulate their plants? And the answer is yes, we do. I go, all right, you collect data? No. You collate data? No. You do mass balancing? No. You do inference? No. Do you do fine operational variables? We don't know. There's someone who does it. Do you model fit? Oh, yeah, that's part of the simulation. So you just simulate? Yeah, that's right, we simulate. So they don't feel a necessity to collect data or to marry what the simulation is doing with the actual data of the plant. And in fact, one of the participants at my recent course got very upset because I was explaining all the various other steps, and he mutinied halfway through and goes, "But I just want to simulate. I just want to be a resident expert. I just want to run a simulator." So there's a certain element of cargo cult mentality, which is quite dominant. So with data collation, it's really using an Access database and explaining them how to do it, trying to explain the concepts of automation. We talked to some participants, well, too many participants, say basically for their job they just cut and paste in Excel, that's all they do. In order to get reports, you explain that all that report writing can be automated if they wish it to be done, and they don't believe the company would be interested. And you actually talk about the lost opportunity in writing a report when you really want to make a decision as soon as possible. And they agree that the companies lose millions of dollars through lack of automation, but that is the company culture. So mass balancing is something I'm presuming all of you are familiar with. Yet recently when I gave the course, and this was to professional engineers in the mineral processing, only 10% knew what I meant by mass balancing. And if you actually, those who do know how to do a mass balance wouldn't know how to actually do a single unit mass balance in Excel without using a software system. So you actually explain to them how to use Excel solver. And it was actually through the company's own initiative that they asked me to spend a whole day on mass balancing. Now, many of you are familiar with, I didn't really specifically talk about it in my background, but I have worked on a number of commercial software developed by JKMRC and JK Tech, including JKMRC. Now, if you do mass balancing, you'll ultimately hit the issue of inference. Basically, when I was a PhD student, I was asked to write a mass balance system, and they said it's a minimization of least squares. And I really think it took 2 weeks. It really wasn't difficult. And then they go, "Oh, by the way, we don't know solid flows." Okay, I think it can handle it. By the way, we don't know this variable. By the way, we don't know that variable. So it became a battleground, in which case there were no winners. But basically, the mineral processors have a mass balance system, and they also don't want to, they want to minimise the amount of measurements that they do. So it always makes it harder for the developer to actually cater to the needs of the user, and also comes to a point where are they missing so many variables that the variables you might be estimating are total bogus. And so you definitely get confronted with this issue of missing variables and whether it's right or how to deal with all these missing variables. And there comes a point where you know that those variables which might be estimated by the mass balance system may not necessarily be valid. And this is a simple case. I believe both in JK Multibal and my own mass balance system, you may very well have size distribution information. You may very well have bulk assay distribution. And it just so happens that the mass balance systems could then estimate assays within sizes. And it was actually when I was given this presentation a year and a half ago in an innovation conference, I actually thought, well, you probably could estimate assays within sizes if you knew bulk assays and size distributions. And I asked the audience if they ever thought about that particular problem, and the audience said no, they had never thought about that particular problem. And so I became more consumed or interested in the issue of how do we estimate all these variables which are unmeasured, and is it possible to do it? So just move on. So the next step is defining operational variables. This is, surprise, surprise, this takes about a day to actually discuss. Because if you look at a lot of simulation systems, the parameters they use in the simulation systems are not operational variables. They're often variables which are of value to researchers. And so, in I have got a sort of market for the simulation system, even through the training courses, whereas I use it. And basically, in the simulation system I've developed, the user can specify their own operational variables. So they effectively create their own simulator and their own interface. So that means they have to really discuss what the operational variables are. And yes, it doesn't take a good day to discuss in a workshop environment. So I've already explained that one of the bottlenecks for a general simulation structure in a mineral processing plant is data collection. The other bottleneck is model fitting, which here includes the actual unit models. But I think, again, it came across in a course I gave, that I actually was talking to the participants about fitting the parameters for a particular model. And it then dawned on me that they had never actually done numerical mathematics at university. So they really didn't know how to create an algorithm to fit parameters to models. And I also realised that there was no way that I could teach it satisfactorily, because it really does require a few days of mathematics. So with model fitting, I think the philosophy, which I think is a good philosophy, of users adding their own models, starts to break down because those who introduce the models actually don't know how to work out the parameters of the models. And we'll see that this is a key issue, and one of the reasons why I think people haven't realised this paper beforehand. So all I do in the model fitting bit really is just get them to look at a simple unit model, calculate the parameters using Excel. Those of you who know me from my previous time at JK, you will know that I hate Excel Solver with a vengeance, but I have to compromise and get them to use it. But I can provide almost the simplest equations, anything with an exponent or log, and Excel Solver breaks down. So you can actually get it to sort of function with the course. But one of the issues is even finding something which is near free and easy for participants to use. And it's getting to a point I may have to provide my own solver for Excel. So in step 8, it's actually the simulation. Once you have all the other steps, simulation is easy. And what I want to convey here is that simulation itself is only a small part of the whole strategy. And then, of course, I discussed optimization. Now, in terms of optimization, engineers, typically, if you ask an engineer what you do in a mineral processing environment, they say they optimize the plants. And in my opinion, it's quite an overused term. I know what they mean. But to me, optimization has a mathematical meaning in operations research, and it's the finding of the maximum value of the target variable. For example, profit, given certain constraints. The operations research concept has various alternative labels such as management science and decision science. So once you understand the idea of mathematical optimization, you actually want to limit the user interaction with the simulator. You want an optimizer which actually does the optimization. And really, you can't optimize a circuit unless you have financial data. So your objective is to maximize the profit. So getting the basics right. So once simulation is understood as a total system, we need to make sure we have the basics right. So what I'll highlight here is the data structure, and where does inference and probability theory fit in? So, as you can see from the diagram at the bottom, I advocate a particle-based model, a multi-mineral particle-based model. So we need to differentiate all properties from unit properties when it comes to simulation. For example, if we say kinetic rate, well, in some limited simulation models, that might be of value. But kinetic rate itself is a combined property of all characteristics and unit properties, which is why in B9 they like to use inherent floatability to differentiate, and they try and avoid kinetic rate, which is itself as a derived measure. I use a particle-based system because particles are real. They are, that is in fact what's being processed. So if you actually, I use multi-mineral particles, which means a particle of a particular type. If you have two particles of the same type, they will have the same behaviour when they go through a circuit. The two things I need to clarify, because there is elements of confusion. When I talk about a particle-based model, people think that I'm talking about simulating 2 billion particles running through a simulator, which is more of a fundamental type of approach. But that's not the way I'm doing it. It's still very much similar to the JKMRC type approach, where you're looking at a distribution. So the question is, how many particle types do you need per size class? And just to give you a rule of thumb, it's probably about 200. So behaviour is the way particles get processed. And we could actually say that behaviour means probability. So if we have two different particles going into flotation, they're not both going to go to the concentrate. They have a probability of going to the concentrate. And that probability may be the same. Hence, there is a strong connection between mineral processing simulation and probability theory. And here we see a picture of a multi-mineral particle in detail, and it just doesn't make sense to me to try and model that as a series of binary particles. And it opens up lots of flaws in both the analysis and the simulation. So, when we think of phenomenological modelling, which is something many of you are familiar with, and probability modelling, which is where I'm coming in from, both methods are complementary. They're not really in conflict, although often people see that there is a conflict when it doesn't exist. If you actually review the literature in comminution, cyclones, flotation, there's a strong basis in probability theory. And yet, by the time it's taught, that connection is often lost. And so probability theory is not taught at appropriate level of depth to mineral processing engineers, which is inclusive of chemical engineers and mechanical engineers. When you now give a course about mineral processing, you would expect those who've got formal mineral processing engineers training to be the minority. And also when students are taught, there's a poor distinction between statistics and probability theory. And so I think for many engineers, when you talk about probability theory, really what they're thinking about is throwing a coin, heads or tails, or perhaps a pack of cards. So here I'll just quickly discuss how probability relates. We have large composite particles, they're broken in the ball mill, and you get these progeny particles. And you can ask the question, what's the probability that, say, this particle is formed from that particle? And technically, that's called the kernel. So, for those who are familiar, I dedicated a number of years to this problem and trying to work out the relationship between these particles and the feed particles, and I approached it from a probabilistic viewpoint. Similarly, when we have flotation, we have particles going into the float cell and particles coming out, and they have a probability of going to the conical table. It's just obvious. The problem is, I've already said that I want to use multi-mineral particles. And so this raises the question of how we're going to use multi-mineral particles. Am I advocating a detailed mineralogical analysis of the whole plant, in which case it can prove very expensive? Well, the answer is I'm not. I see the distribution of multi-mineral particles as a microprocess. And what we see is a macroprocess. These are my own definitions for this particular seminar. But a macroprocess is where we're looking at observables, and a microprocess is a process largely hidden to us that we know affects the macroprocess. Microprocesses don't actually have to be measured, but can be inferred from observable variables. Now I'm going to take you back over 100 years to one of the greatest mathematicians, Ludwig Boltzmann, who developed inference methods, the founder of inference methods and the mathematical use of entropy. And he concluded that there existed atoms. Now, if you look at this photo of him, you can see that he's not a very happy person. And he actually did suffer from depression, and he did eventually suicide. But there's a question mark over whether or not that was related to his professional career. But the reality was that he believed strongly in his mathematical theory of understanding atoms by looking at the macroprocesses at that time. And in his view, well, it just seemed that the physicists rejected atoms at that time. And so poor old Boltzmann was stuck in a section, horror, called applied mathematics rather than physics. This is also evidence, of course, that it was applied mathematicians who provided the great breakthroughs in physics. I don't know how many physicists are out there. Anyway, he came up with a mathematical formulation for dealing with entropy, but it wasn't really till a completely independent person, Shannon, in the 1930s, founded information theory, which he originally called the theory of communication, where he was actually dealing with the whole problem of missing data in signals. Now, it so happens that I have great difficulty believing this story, but it is a classic. And it's on Wikipedia, so it must be right. But basically, he had this formulation for missing information, and he didn't know what to call it. He had a measure of missing information. Now, it so happens that he was a friend of von Neumann, the great physicist. And von Neumann asked him how he was getting on with his new theory, and he said he didn't know what to call missing information. And von Neumann said to him, call it entropy, because there's a mathematical development very much like yours, which exists in Boltzmann's statistical mechanics, which I also think should be called probabilistic mechanics, but anyway. And in the second place, no one understands entropy very well, so in any discussion you will be in a position of advantage. Now, when you actually read the literature about the effects of this particular changeover and using entropy to describe a probabilistic method of estimating missing information, there's a lot of negativity about Shannon relenting and using entropy, because it now mixed in a probabilistic technique with statistical mechanics, and people feel obligated to try and understand what I would call probability entropy and how it relates to statistical mechanics, and therefore becomes quite complicated. But in 1951 was another mathematical development, which is only a variation of Shannon's, where they introduced the idea of a prior. And the formulation was as follows. Now, if you actually analyse it, it really isn't that big a deal. It's basically saying the probability must be between 0 and 1, and unless I have information to the contrary, the real probability would equal the prior probability. So the point here is, however, that when you look at this equation, you realise that this could very well be the basis of a mass balance system. So a prior is a belief in the absence of information to the contrary. the variables are adjusted from their priors to satisfy fixed constraints. So we could have used the Kullback-Leibler divergence for mass balancing theory. And then there's issues about what you do if you have a missing variable, and you can still use a prior, which is called an ignorant prior, which you basically say all the variables are the same value, unless I have a reason to think otherwise. But it was in 1951 that mineral processing could have, if you like, evolved and encompassed the Kullback-Leibler divergence and developed mass balance systems based on information theory. But instead, the mass balance systems were pretty well established in mineral processing. They kept going with the least squares minimization. Now, I could talk about the whole issue of least squares minimization for a number of hours, and it's something which I have great passion in, not necessarily you. But basically, my open position is that the use of using least squares, I will be strong, is fundamentally a total waste of time and completely inappropriate, particularly when you don't know what those standard deviations are. It's just silly. So if you don't actually know what the standard deviations are, it would therefore seem reasonable that a mass balance system should be based on information theory. And that is the path I've gone down. But if you're using information theory, you're automatically setting up a framework whereby you can actually estimate the missing variables. The trouble then remains that even so, the measured variables may be so uncertain as to be rendered impractical. Well, they can still be bogus just because you're using a mathematical theory. It doesn't necessarily make the method valid. Yet on the other hand, you may be missing an opportunity. You could in fact be estimating these missing variables in such a manner that they're practical. So this increased functionality of inference has to some extent caused general uncertainty. And this is not good. So the problem becomes, how do we improve the certainty of estimating our unmeasured variables? And this was the variation, is you can actually use all variability to advantage. So if you have information from different orders, and this is what I painted, then you actually say, well, unless I have any information to the contrary, we know that the particles going through the second orbit, their behaviour is the same as in the first orbit, and same for the third, fourth, and so on. So you have this prior belief that the particles going through the units should all behave the same. In this process, you've now linked up all these different order data together. So now comes the surprising benefit. Because we're linking information from different plant orders of the same plant, and they're now integrated, we actually need less measurements per order. Thus, all of a sudden, your certainty in all these missing variables becomes far more certain. So here is a schematic, which is only a schematic, don't take these numbers seriously. But this type of approach of linking data from different plant orbits together provides a methodology where for a given cost you can get far more accuracy, or if you specify a particular accuracy, you can do it at much less cost. So in the particular patent itself, I imagine a number of you have written patents, but the patent itself, you have to actually make it as broad as you can and put in as many subclaims as you can. So I made numerous subclaims in the patent. There's actually about 12, but and it's actually I think it is the longest patent that the patent attorney has ever gone through. But basically, I put in there, in more colloquial language here, we do not need assays within sizes. Head assays and size distributions are sufficient. For coal, we don't need to estimate density distributions or washability curves. Average density for each size class is sufficient. We don't need detailed mineralogical data. multi-mineral particle distributions can be reconstructed from the data. So, does this mean that I'm advocating not to perform detailed sampling? Well, the answer is yes and no, which is a good political answer. But basically, well, you don't have to perform detailed sampling because you may not need to. But on the other hand, the more measurements, the better, and does indeed allow better identification of problem units. But just because you might have one problem unit and you want to sample that in great depth, doesn't mean you have to do that to the whole plant. So the information theory method, or the MIDAS tech method, provides the basis for strategic sampling, and therefore in the course there will be far more dedicated to the whole issue of data collection. In the course itself, I go into various mathematical methods. Monte Carlo simulation, most of you would be familiar with that. Markov chain Monte Carlo, which is something which I've actually published in papers when I was at JKMRC, but I do provide very simple explanations of it and how to deal with multi-mineral particles, because the jump to multi-mineral particles is not that onerous if you're prepared to just spend a couple of hours thinking about it. Similarly, this actual method of using all variability to advantage is highly related to hidden Markov models, again a probabilistic method. So these diagrams here explain how our approach is different to traditional. So in traditional modelling, you have your observable law properties, you create a unit model, and you have your output observable law properties, and you have various operating parameters which you fit or no. But in this type of approach, you actually are looking at the observable law properties, but going deeply into the data. You are actually understanding the micro level of the particle properties. From those particle properties, you construct your unit models, for which now you create your hidden or microscale level output law properties, from which you can get your output observable law properties. On one hand, people think this is complicated. On the other hand, it actually makes everything simple. So our software, if you like, you don't have to, as a user, if you were to use our software, you don't have to be exposed to all these hidden law properties. From your viewpoint, all you're still seeing is the input observable law properties and the output observable properties of the unit models, and the maths is doing all the work. So, and in fact, that's an expression. I'm actually getting a higher success rate from industry on their understanding of these methods, and they come up with catchphrases like one is, let the maths do the work. So in the traditional modelling approach, this is actually SGS all over it. When I was at SGS, I was asked to review their flotation analysis software, and they said they get a sample, they put it through a series of flotation cells, and they measure the outputs, and from that they construct information about the oil properties. So it was sample, output, estimate, sample, output, estimate, and so forth. And I said, but hang on, you're actually putting them through the same flotation cell. So if you actually differentiated the oil properties from the flotation properties, we would use those flotation cell properties as a constant. So here it's just a very subtle change in the diagram. You're saying they're going through the same unit model. And all of a sudden you now compare how the samples are processed. So if you have one sample with more NSG than another sample, you actually compare it and you can work out what the entrainment is. And that's all quite obvious, I believe. It's not utilised anywhere in any flotation service, which is rather mystifying, but that's the way it is. But so it's basically the idea of different samples. We know they're going through the same unit model. And then it was actually, I realised that unit model could in fact be a plant. So we know that all variable type 1 is going through the same plant as all variable type 2. So it's invariant. And so that was how this methodology came about. So I'm actually going to do a bit of skipping. So here we see the where the benefits of this particular approach come in. So if you were to use the traditional approach of detailed sampling, yes, you should comfortably be able to say that you will improve plant performance. This is an extreme type of viewpoint, it's not what I'm advocating, but if you were to do it this way, you would say measure less information, and you may indeed also increase the profit, but not as much as if you've done detailed sampling. But if you do it a second time, a third time, and so forth, then for the same net cost, you've actually moved into a higher profit regime. This is particularly important for if you're doing some sort of online system and you're linking it in with our software, you actually get time value. You can actually make operational changes in short time frames. So here I'm just going to work through density separation. Now, if you look at the literature, this is a partition curve, so it's the probability, in this case, a particle will go to the lights, but I'm more comfortable saying probability of a particle going to the heavens. But you see a partition curve. Now, this particular paper by London Benter goes into great detail about the partition curve and how you have to do float sync tests on the feed, the heavies and the lights, in order to get points on that graph and then work out how to fit your EPs and your 50. But when you look at it mathematically, this is one form of the partition curve. There are, in Peter King's book, he gives 7 particular equations, but this is the one I'm most comfortable talking about. If you actually look at the equation, your unknowns are rho 50 and EP. And I've seen too many times people thinking they have to do float sync tests. But if you actually looked at it from a mathematical viewpoint, you can actually, from a mathematical viewpoint, simplify it, and you have 2 parameters, A and lambda. Now this particular equation can be derived from information theory. But a mathematician would look at this and say, all right, there's 2 parameters, we need 2 knowns. So if we did know the feed float sync, then we don't need the heavies or the lights, we just need to know the average density of the heavies and the lights. And that gives us 2 pieces of information, and therefore we can estimate the 2 parameters. And again, I think one of the reasons why this hasn't been popular in classic mineral processing is because students are not taught model fit. They're actually not taught how to fit these parameters, given just densities. And that's why we do it in the course. So I actually spend, I presented this in the course, and the facilitator said, oh no, we need to do this. So we got out in Excel and actually used Excel solver and came up with it. And after 3 hours, they go, yes, you're right. That's the way to do it. And so it's in the course that we actually get down into Excel and work out these things, because it's actually not something they're exposed to. Then the variation is, what about, we don't have to focus so much on that. Just, if you actually had 2 different feeds and you knew what those feeds were, and then you put them through a cycle, what do you actually need to measure in order to calculate the parameters of the partition curve? You actually don't need average densities. Does anyone know what you do need? You only need 2 parameters, there's only 2 parameters, you only need 2 pieces of information. So all you need is the flow rates of the products. That's all you need. And I actually realised this in when I gave the course. They gave me a weekend to prepare for the second part of the course, and in that weekend I go, well, you only need 2 different feeds and you can estimate them. And then I showed them on the Monday and they go, we don't believe you. So he spent 3 hours going through it. That process of spending that 3 hours, they then understood everything. Okay, they understood, wow, you don't actually need to measure directly what you want to know. It can be inferred. So now here's the interesting one, which Tim will realise is a basis of an ACART proposal many years ago. But basically, we're trying to submit an ACART proposal. But basically, this was almost a thought experiment I did on a computer about a year ago, where if you did in fact have 2 different feeds and you did actually measure your mass recoveries and your densities, you can actually start to get rid of information about the feed. So I got rid of the actual original distribution of the feed, and then did a back calculation to try and work out the washability curve for the feed. So I start off with a known feed, I go through the process, a known partition curve, estimate the heavies and the lights and the average densities, and then just use the average densities and the mass recoveries and back calculate the feeds for the washability. Back calculate the feed. So feed A is the original feed, and feed A estimate is that done from the back calculation method. And as you can see, I think there's reasonable correspondence. But now, a metallurgist may well say, but that's not good enough. Well, this is where there's a conflict. If you actually realise that this is just a first step, then it's good enough to actually simulate how to improve the plant performance, and then that takes you to the next step of the optimisation, from which you optimise again, and so forth. So obviously it's better to do as much sampling as you can, particularly in the first instance. But the idea of incremental improvement is you're not trying to do just one hit at optimisation, you're trying to do it successively. Yeah, well, I have. I've been a good boy. So, there was a case I did want to present, but I wouldn't have been able to do at the time. It is available in what I call the Las Vegas presentation. So those who are interested, just give me a card and I'll send you the link. I possibly should have put it in here. But basically, it's dealing with the whole issue of multi-mineral particles. And I'm putting forward the idea that if you're doing a succession of plant audits, and in this case you did know the feed, then all you would need to do would measure the flow rates in each size of the products. It's not to say, because it would be silly in this case not to measure something about grade, but I'm putting it as a thought experiment that indeed you don't need to measure it. And this is the results. So I use particle types. These are I have a model with the particular recovery of the particle types and I calculate it. And as you can see, it's a very high correlation. And I do have sleepless nights wondering whether I, in some ways, read this, but I haven't. You look at it, no one's going to believe you, the correlation's too good. I'll go through it all now. It's all been done legitimately. So, the opportunity is there. Here's a conclusion discussion. Particle-based structure is the real structure for modelling processing plants. The particle-based structure does require advanced mathematical methods. Simulation should be seen as part of a total solution. The cost savings of applying a simulator as part of a total solution is potentially huge. It is possible for users to develop models that can be easily integrated into the simulator. And just a comment that even though multi-mineral seems complex, many existing models can be adjusted for particle-based structures and multi-mineral. So the action plans, I would encourage you to enroll in the course, that's your decision. I do believe that we are ahead of the game and it would be beneficial for you to attend. We would certainly welcome opportunity to work with JKMRC, particularly at the level of validation of a lot of these concepts. And for those of you from industry backgrounds, and there's a number here, we just want to go ahead, and I hope you do too. I am a good boy. I do acknowledge JKMRC wherever I go, because they did provide the foundational basis for me to develop these concepts. I do acknowledge the P9 series and JK Tech. SGS was huge in my understanding of the value of these methods. And then there's just a lot of people who have helped. Dave Wiseman, Michael Hayes, Basdu Rupal, and Bill Whiten, you all know. And as a final, I get heaps of help from LinkedIn. And if any of you are active in LinkedIn and you're one of these helpful peoples, then you also get thanked.
Well, thank you, Stephen. I think we'll just grab maybe one or two quick questions and continue maybe discussion with the coffee and biscuits. So, are there any questions?
we all know that this mass balance is very important, and also we talk about a lot of mass balance. Maybe you don't know, like a simulation already move into the liberation domain. For liberation.
Oh, well, that's what multi-mineral particles are. That's liberation.
But actually, probably we know liberation is not. It's not like a mass balance. Because mass balance is like a mass conservation.
So you're gonna have to.
Maybe not here clear. We also have the theory and the law of mass conservation, but the liberation itself is not balanced. So.
Well, no, you can mass balance liberation. Why can't you mass balance liberation? Yeah, it's still it's subject to the laws of conservation as well. That's the whole concept. A particle going into a flotation cell must come out, so mass balance is conserved.
That's for flotation.
Well, yeah, and yes, it's not. Liberation itself is not conserved in a comminution equipment, which is what I showed. Yeah. Well, so what's the question? Yeah.
Well, as I said, we can continue. Are there any questions? No? Okay. Well, thank you, Stephen.